Okay, so a soft toys manufacturer continuously carries out quality control testing to uncover defects in its products. After testing a large sample of its products, the manufacturer found the probability of a soft toy having poor stitching is 0.03, and that a soft toy with poor stitching has a probability of 0.7 of splitting open. So this is conditional probability. So it will only split open really, or the possibility of it splitting open is only higher if the stitching is poor. So that's what we would call conditional probability. So given that the stitching is poor, the toy has a higher chance of splitting open. A soft toy without poor stitching has a probability of 0.02 of splitting open. So obviously we can see much lower. Okay, so let's do our tree diagram for this. So we might start with, we'll say bad stitching, good stitching. Now, the probability of the soft toy having poor stitching, so bad stitching, is 0.03, and good stitching would be 0.97. So a much higher chance that it's actually fine. And then it can either stay closed or it opens. So opens or closes, opens or stays closed. Now, if the stitching is bad, we're told that the splitting open is 0.7. So staying closed is 0.3. So it has quite a high chance of opening. If a soft toy doesn't have poor stitching, so in other words, it's good, it only has a probability of 0.02 of opening, which means it has a high chance, 0.98, of staying closed. So that's the first part of that question done. So we've represented that and we've shown the probability on each branch. So use the tree diagram otherwise to find the probability that a soft toy chosen at random has exactly one of these defects. Now, exactly one means the stitching is bad, but it stays closed. Or the stitching is good, but it opens, because we're only allowed to have one problem with the toy. So you can't have bad stitching and opening, because that would be two defaults. This is exactly one. Now, as always, we multiply across the branch. So I multiply 0.03 by 0.3. And then I do the same on the bottom, 0.97 multiplied by 0.02. So I end up getting the two of these as my answers. And then, of course, we multiply across the branch, but we add down the tree. So when I add down the tree, this is my answer. So it's a pretty low enough probability that you have just exactly one fault. Okay. The manufacturer also found that the colors used in soft toys can fade. The probability of this defect occurring is 0.05 and is independent of poor stitching. So the fact that the toy can fade has absolutely nothing to do with the poor stitching or splitting open, which makes sense. I mean, the color would have nothing to do with those aspects of the toy. So a toy is chosen at random. Find the probability that the soft toy has none of these three defects. So we're going to have to go back up and include the color in our tree diagram. So the probability of the color fading is 0.05. So not that high. So fade or not. So 0.05 that it could fade. So that means 0.95 that it's not going to do that. And that's going to be the same for each one, because this is not conditional. This is independent. What happens before the stitching and the opening have absolutely nothing to do with the fading. So each of these branches is going to look the same. Oh, sorry, I forgot the zero there. My apologies, go back there a sec. Zero, just do this a little bit thinner, 0.05, 0.95, and again, 0.05, 0.95. Now, once I have my diagram filled out, the question was, sorry, the probability has none of the three defects. So none of the defects. So if we go back up here, if it has none of the defects, we're looking for good stitching. We're looking for the fact that it stayed closed, and we're looking for the fact that it has not faded. So that's the branch we're interested in. And as always, we multiply across the branch. So I'm going to multiply the 0.97 by the 0.98 by the 0.95. So that's what I'm going to fill in down here. 0.97 by 0.98 by 0.95. So that gives me this. So when you look at that result, that's quite high, isn't it? So there's quite a high chance there's actually absolutely nothing wrong with the toy. Find the probability that the soft toy has exactly one of these three defects. So we're looking for exactly one of the three defects. So again, I'm just going to scroll back to our tree diagram. Now, exactly one. So I'm going to just change my highlighter here. We'll do, what happened? We used blue. Okay, so we'll do blue. Right, so one defect. So bad stitching would be one, but that means it has to stay closed and there's no fading. So that's one possibility. Another possibility is that the stitching is good, but it does open, but there's no fading. So that's another possibility, one defect only. Or we have a possibility that the stitching is good and it stays closed, but it does fade. So that's my last one. So there are my three. So I'm going to multiply 0.03 by 0.3 by 0.95. Then I'm going to multiply 0.97 by 0.02 by 0.95. And then I'm going to do this one. So I'm going to multiply 0.97 by 0.98 by 0.05. So that's the last part of that question. So I hope that makes sense there. So I'll just write that in 0.03 by 0.3 by 0.95. So I always multiply across the branch. And when I'm done multiplying across the branch, then I add down the tree. So my three answers are these when we put them into the calculator. And adding them all up, this is what I get as my final answer. So I just add up those three branches. Okay, and that's that one done.